Okay, welcome everybody. Thank you for coming tonight to the Lunar and Planetary Institute for this evening's presentation. If you're online watching us, welcome. Glad you could join us. My name's Andy Shaner, the Public Engagement Lead here at LPI. Tonight is our fourth presentation in our current series, diving into ocean worlds. The topic is Titan, so this should be fascinating. We heard a little bit about it in our last presentation, but Dr. Lorenz was kind to not say too much. Our fifth and final presentation will be covering the TRAPPIST-1 system, extrasolar system that was, the star was discovered a while back, but the plans were discovered a couple of years ago. And our speaker will be one of the discoverers, Dr. Sue Lederer, who's actually at JSC. But she is trying to nail down a date to go to a telescope to do some observing. So once she has that, we can get a date for our presentation here. I can't tell you it'll be April or May. So, one of those 2 months. I'm glad I could narrow it down to 8 weeks. We'll also announce the our topic for our next series, starting next fall, during that evening. Some of you folks, when you come in, I notice you'll check out our wall of time down the long hallway here on the first floor. If you went and looked tonight, you probably noticed there's some stickies on it. We're actually in the process of updating the 15-year-old wall of time that covers 4.5 billion years. So we're doing it on the cheap. We're just putting up stickies and leaving them there. We're trying to become a little more efficient. No, we're actually going to print them and remount them. So when you come back for our next presentation, that will be updated. So the challenge is this. Oh, that won't work because it tells you what we're updating. I'm going to say the challenge is to figure out what we updated when you come back, but you can go look now to see what we're doing. So never mind. If not already on our listserv to learn about our future presentations, you can sign up by the front doors when you're leaving today. It'll be on the table to your right. And on the table to the left, we had some handouts, but we also have a stack of very quick 3-item surveys. If you could just take a few seconds to fill that out, it'd be much appreciated. Teachers, if you're with us, we have professional development certificates for you at the front desk. So please grab one of those before you leave. And right now, I'd like to bring up Dr. Louise Proctor, our director, to introduce our speaker.
Sorry, Joe. Hello. Right, very excited tonight to welcome our speaker, Dr. Ralph Lorenz. Ralph started his career as an engineer for the European Space Agency, where he worked on the design of the Huygens probe to Titan. From 1994 to 2006, he was a planetary scientist at the University of Arizona. Since then, he worked at the Johns Hopkins University Applied Physics Laboratory, and we actually worked together for about 10 years there, so we know each other well. Ralph's activities have centered on Titan, both using the Cassini Huygens data, but also future missions. He's going to mention one of those tonight. It's pretty exciting. But his interests aren't exclusively focused on Titan. He also works all over the solar system. He's done work on Mars, Venus, dust devils, sand dunes, planetary climates and landscapes, and, if that wasn't enough, aerospace systems. He is the author or co-author of several books, as well as over 200 publications in refereed and popular journals. And so it's with great pleasure that I welcome our speaker tonight, Ralph Lorenz.
Well, thank you, Louise. Thank you all for coming. It's always a pleasure to talk about Titan, which, as Louise mentioned, has really been the central focus of my entire career. Just to get me oriented, how many of you heard some of the earlier lectures in this series? Okay, so you're all completely up to speed on icy rings. So Titan is different. Titan is special, and I hope to convey why that is. This background picture is an image acquired by Cassini, looking across the rings. Titan is in the background, and I forget which moon this is, Prometheus or something. I imagine I'm not going to be able to cover in 45 minutes all that I'd love to cover. The scientific output, mostly from Cassini, but also ground-based telescopes and the laboratory efforts and so on, pertaining to Titan, has been at around something like 100 scientific papers a year for the last decade. I mean, the amount of material we have learned and are continuing to learn about Titan is tremendous. So anyone who wants to follow up with me, my email's there. I'm easy to find on Google, so don't be shy. Just to set the stage, Titan can be actually considered as in many ways it's even though it's strictly a moon, it's more of a planet than some planets. It's bigger than the planet Mercury. The distinguishing feature, of course, is that it has a thick atmosphere. It's the only moon in the solar system with a thick atmosphere. It has a gravity about the same as our own moon. The tilt of Titan's equator and Saturn's equator is not too different from our own and that of Mars. So Titan has seasons. Come back to that. The atmosphere is about 4 times denser than the one we are breathing today here, and is also mostly nitrogen. Titan doesn't have free oxygen, but it does have a few percent of methane, and the methane behaves as water does on Earth. Titan, being so far from the sun, is much colder. Water is frozen up as ice on the surface. It may be water in the deep interior, liquid, but at the surface is hard as ice. The sunlight at the surface is 1,000 times less than Earth because Titan is 10 times further from the sun. So there's 100 times less sunlight falling on the top of the atmosphere. And the atmosphere is very hazy, so only about 1/10 of that filters down to the ground. Now that's still 1,000 times brighter than full moonlight is on the Earth. So there's plenty of light to see. Weak winds. Titan rotates synchronously, like our moon does about us. So the same face of Titan always faces Saturn. Just as a size comparison with the other icy moons, there's Europa and Enceladus you've already heard about. Titan's optical diameter is actually the largest in the solar system, but its solid diameter is just a hair smaller than Ganymede. The thing that makes Titan really fun and in many ways an Earth-like world is that it has an atmosphere with a hydrological cycle. Methane, as I said, plays the same role water does on the Earth. It forms clouds. The clouds rain down onto the surface, forming at least ephemeral rivers. There are surface reservoirs we'll come back to. This hydrological cycle has a second component to it, which is that some of the methane leaks up into the atmosphere and is destroyed by sunlight. And the fragments recombine in all kinds of different ways to make tons of different organic compounds. Ethane is a liquid. Most of the others are solids. The hydrogen that's liberated escapes to space, so that this is a sort of open cycle. But there's a lot going on, as we'll come back to. So Saturn's orbit around the Sun takes 30 Earth years. And in fact, the orbit is slightly eccentric. The perihelion is about 10% closer than the aphelion. So Titan and Saturn get about 20% more sunlight near perihelion than they do at aphelion. So the seasons are asymmetric, and that turns out to be very important, as we'll come back to. The length of the Saturnian year more or less sets the timescale it takes to get out to Saturn. And Cassini was launched in 1997 and arrived in 2004. Basically one Saturn season to get there. It was designed to operate for 4 years, and in fact it worked so well we extended the mission by 2 years to the northern spring equinox, and then Cassini was extended once again for another 7 years, a whole Saturn season up through the summer solstice. And as you probably were aware, the Cassini mission was ended in September 15th this year by plunging into Saturn's atmosphere. Now this sort of 30-year timescale is it's an interesting timescale from a human perspective. You can sort of lay out your prominent life events. I am 1.5 Saturn years old. I started working on Cassini as a young engineer straight out of college in 1990, and at 4 different institutions in 3 different countries over 27 years. I've worked on the same project, not full time all the time, but that sort of continuity, the friendships and relationships you build over that period, really form a big part of your life. You can lay other things out on the same time scale, and you'll see a number of these books popping up at different points in the talk. Many of them pertain to Titan, so there's more you can learn there. And if you're interested in the hardware, the spacecraft itself, last year I published an owner's workshop manual that really gets into the nuts and bolts of the spacecraft and how it was built, designed, and operated. Because it's a magnificent machine. I don't have time to talk about it, but one of the most complex and largest space missions launched by the United States and its international partners. So one of the fun things about bringing an international project together is that there are different ways of working, and there's actually a sort of institutionalized pork barreling that happens in Europe, wherein so if your job as a project manager to make the Huygens probe, that's the European element of Cassini, if your job is to make that that thing happen, then just give it to the Germans. They'll take care of it. It'll work great, right? But what a European Space Agency project manager has to do is give 20 to 25% to the Germans and 25 to 27% to the French, and find 3% of the project for the Belgians to do something, and 5% for the Finns. It's got to be parceled out. The way the European Space Agency works is each member state must get back contracts in the same proportion as they fund the budget. So there's some interesting challenges there, and it's it's a little bit like one of those jokes where hell is where the police are from wherever, it's Italy, and the cooks are from England and all that. But all these bits come together. The parachute was from the UK. The heat shield was based around French ballistic missile technology. The structure was from Spain. The radar was from Finland. And all these countries are working together. All these interfaces have to be figured out. And this is one reason why this sort of engineering is so expensive. Is you might see here some people assembling a spacecraft. Well, somebody had to figure out that this Spanish structure had to mate with this French heat shield, and it has this Austrian dolly to hold the bits together so the bolts will line up. And then somebody had to realize that this door has to be big enough for this dolly to go through at this facility in Germany. All those interfaces have to be figured out years in advance on paper. And actually at the time it was paper. There wasn't electronic document sharing in the same way there is today. And I remember as a young engineer straight out of college, when there was a 20-page update to the experiment interface document that was faxed. Remember faxes? Faxed from our prime contractor, Aerospatiale in Cannes. It was me that had to run down to the fax machine and phone them back and say, resend page 15. Xeroxing documents was interesting because the probe had 2 significant experiments from the USA, and the US instruments were all built in rather odd. The project requires you to use metric units, but everything's 2.54 centimeters, and these 100-page documents were on 8.5 by 11 paper, which won't go into the A4 European photocopier. So all these things have to be figured out, and there are language problems and all that. So it's it's a huge enterprise to bring all these pieces together, and ultimately deeply fulfilling. Anyway, Cassini was built, was launched in '97, took 7 years to get to Saturn and Titan. And one of the things we expected to find was this methane story of methane breaking up in the upper atmosphere and forming other stuff. We had no idea how complicated that stuff was going to get. Some of you have heard Jonathan Lenine talk about mass spectroscopy in Enceladus. The mass spectrometer on Cassini was principally to study Titan. And if you were flying past the Earth, you'd see maybe 2 or 3 little spikes here. There'd be nitrogen, there'd be oxygen, maybe some nitrous oxide, a bit of helium, something like that. But there's dozens and dozens of compounds in Titan's upper atmosphere. And this is 1,000 kilometers above the surface. So the chemistry is getting very complicated very, very early. The Titan is a factory of organic material, carbon-bearing material with nitrogen and hydrogen. Cassini arrived in July and made a couple of orbits around Saturn, flying by Titan a couple of times before it released the probe actually on Christmas Eve, Christmas Eve or Christmas Day, depending on which time zone you're in, 2004. The probe was powered by batteries and just was basically in sleep mode for a coast of 3 weeks. And then it hit the upper atmosphere of Titan at 6 kilometers a second, Mach 25. The outside got cooked to 1400 Celsius, but that's what the heat shield's for. And then the parachute popped out at Mach 1.5, and it took the probe about 2.5 hours to parachute down to the surface, which it hit at about 5 meters a second. That's actually very convenient for testing because 5 meters a second is that. Now, I was very fortunate. As a grad student, I got to build, as part of my PhD research, a little part, sort of discrete, separable part of Huygens, an instrument called a penetrometer. So it's basically a little force sensor the size of my finger that generates a charge when it's pressed, and it's stuck out of the bottom of the probe. And so when the probe landed, this was rammed into the ground and generates a force history. And you have to figure out, how much force to measure, how fast, how do we calibrate it? This thing's got to work when it's at minus 180 Celsius. How do we check its status in flight? The material we use has to be tolerant of the radiation in space. All this stuff has to be figured out, and that's what you pay engineers for. Actually, there's a really nice documentary about the experiment that this sensor was a part of. My PhD advisor, John Zarnecki, as a child, got to see Yuri Gagarin when he visited London after his first flight, and he went on to become a space scientist, and then was involved in this experiment on Huygens. And this documentary really tells that story very nicely and the challenges we faced developing the instruments. So as a grad student, testing this instrument into different materials to show that it will tell us something interesting. These are force histories with sort of arbitrary units. This is 50 milliseconds, so 1/20th of a second. Basically, that's how long it takes to traverse that far at 5 meters a second. So when you push into dry sand, the grains lock together, and you get this sort of ramping force profile. Wet clay is a constant resistance, and gravel is kind of spiky, with the spikes, height and spacing relating to the size of the particle. Well, anyway, this was all done in 1994 and then put in a cupboard and then assembled with the instrument, put on the spacecraft. I actually found out at the launch site at Kennedy that, in fact, the best unit that we built was broken by a technician during assembly, and it was actually the spare that we sent to Titan. I carry one of these around on my keychain, but you can also go and see one in the London Science Museum, and there's one obviously sitting on the surface of Titan. Anyway, after close to 10 years, I got my 512 bytes, 1/20th of a second worth of data, and was fortunate enough to be with the team at the European Space Operations Center in Darmstadt when the data came down. So we hadn't seen the pictures, right? After all these years, you'd think the scientific teams would get a sort of calm month or two to cogitate on the data and really understand what it was. But no, we got the data on a memory stick at about 6 p.m. On the 14th of January 2005, and there was a press conference at 11. Go. And so we hadn't seen the pictures. We were all looking at our own data, and we had the squiggly line. And guess what? It looks nothing like any of the materials we tested in. But we sort of decomposed it a bit. It's kind of like a constant resistance, like packed snow or wet sand. And there's this spike at the beginning. Is that like a spark that jumped from the surface of Titan to the sensor, or or was there a layer or something hard? We actually came up with the idea it might look like a bit like creme brulee. And the media love that, right? Food analogs are something people can really relate to. And the headline in Nature magazine that week was Titan team gets just desserts with creme brulee surface. Once we'd seen the pictures, we actually think it was probably one of these cobbles that made the spike, but all good. The total descent time was actually at the long end of what we expected, almost too long. And this number 8869.75 seconds was very important because there was a sweepstake on that number. You can just see in the corner here, there's a bottle of Lagavulin single malt whiskey that the destination of which depended on guessing this number right. And actually my PhD advisor got the closest answer, which is probably why he was in charge. Okay, we'll get to oceans soon. Let me just talk briefly about seas of sand. This was something of a surprise. This is a radar image taken by Cassini about 200 kilometers across, and you can see these ridges. The bright stuff is glints off the face of the dune. And these dunes actually sort of behave like streamlines. They kind of go around topographic obstacles. I actually wrote a paper explaining why we probably wouldn't find sand dunes on Titan, which was spectacularly wrong, but for quite interesting reasons. And one of the things that we can use to understand remote sensing data of what's really a very unfamiliar environment is to use terrestrial analogs. And in fact, these dunes are the spitting image, the same size, same shape as the largest dunes on Earth. These are in the Namib desert of the southwest Africa. There's the Atlantic Ocean. This is actually a handheld digital camera picture taken out of the window of the space shuttle in 1994. But as I say, these dunes are exactly the same size and shape, made of different stuff, right? It's not silicate sand on Titan. It's probably organic material. The gravity is different. The air is thicker. And yet somehow these dunes end up being the same size, which is sort of interesting. So you can go to these places and try and understand the processes that are shaping the dunes. This is a ground penetrating radar to look at the layers of sand underneath. The great virtue of ground truthing is that you can not be a nerdy scientist in front of a computer all the time. You can be sort of badass explorer. But the media like this sort of stuff because it's visual, it's interesting, it's a lot more interesting than a computer screen. And you get to appreciate things that are going on planets. The physicists take a very often idealized view of the world. Imagine a spherical cow, and the real world, the real worlds, are often much more complicated. One of the things we've puzzled about is why the dunes on Titan sort of terminate so abruptly. Right? There's a very sharp edge. Why isn't the sand just kind of trickling by? And when you see how the same thing happens in the Namib, turns out it's just an ephemeral river. I mean, there's only water in this maybe a day or two a year, just when there's a flash flood. But that's enough to remove the sand at the same rate it's being transported, and so the dune field is truncated even by an ephemeral river. You can learn more about sand dunes in a dune book. These linear dunes are formed by a wind regime that's sort of alternating. Winds going kind of about 45 degrees to the dune orientation, and then 45 degrees the other way, in the sort of interpretive dance kind of funnels the sand in sort of the vector mean of the sand transport. Now that sand is probably heavy organics, probably nitrogen substituted polycyclic aromatic hydrocarbons. If you must know, there's a term tholin is sometimes used for the photochemical material we think forms in Titan's upper atmosphere that makes the haze, that makes the atmosphere so opaque. Now this stuff is chemically interesting, but in terms of origins of life and so on, is actually a dead end, because there's no oxygen in it. Sugars and amino acids all have oxygen. But it turns out it's actually quite easy to incorporate oxygen in this stuff. You just add water. Now, Titan's surface is too cold for liquid water to be sustainable on a long-term basis. But you'd say the same about molten rock on the Earth. It does happen. Impact melt sheets and volcanism can do it. And when you add water to this stuff in the lab, you can make amino acids, you can make pyrimidines. These are some of the bases that encode information in DNA. And then we don't know, how the miracle occurs from going from these sort of compounds that we exist in meteorites and elsewhere. We know we can make them in Titan conditions, to the functions that execute life. We don't know. And all these steps have been lost on the Earth because whatever vestige of these chemical systems were around were eaten by the living things that subsequently evolved. But on Titan, this stuff is frozen up, and so we can go and investigate it to see how chemical complexity evolved. So we think that there is liquid water in Titan's interior for several reasons. I mean, scientists build models, just work out how much heat is coming out of the radiogenic elements in the rocks. These sort of thermal models tell you the interior should be molten. There was a rather obscure measurement on the Huygens probe that measures a sort of electrical resonance. Basically, the ionosphere and an internal conducting boundary can act as a sort of waveguide that traps a signal called the Schumann Resonance. On Earth, it's excited by lightning. On Titan, it's probably excited by the interaction with the Saturnian magnetosphere. But the assertion was made that there's a signal that was detected by Huygens that is indicative of such a resonance. That implies a conductive lower boundary, that the body of Titan isn't ice all the way down. There's actually a layer of molten water that is electrically conductive. That's a little bit tenuous, but it's supplemented, by several other lines of evidence. This is a partial mosaic of some of the radar images we acquired. Remember, Titan is about 5,000 kilometers in diameter, pole to pole. Most of the radar swaths are about 200 or 300 kilometers across. And they're sort of randomly placed. It relates to how Cassini's orbit around Saturn worked. But you see there's lots of overlaps between the different swaths. Now, the way a radar image is made up is you map the echo time and the Doppler shift to where the spacecraft was, and you say, well, Titan is this big, and its north pole is up here, and it's rotating like this. So those Doppler range pixels map to latitudes and longitudes like X. Now, if you look at the same mountain on subsequent flybys, it should be in the same place, right? But when we made these images, we found that sometimes things didn't match up. And the mountain's in the same place relative to everything else on Titan. The bit that's wrong is the assumption that the North Pole is here and that Titan is rotating just like so. There could be non-synchronous rotation, and there can be polar wander. And both of these things point to the crust of Titan being isolated from the interior by a liquid water ocean. So that confirms the model. There's another dimension, and actually the most persuasive relates to gravity measurements that Cassini made. Because Titan's orbit around Saturn is eccentric, the tidal pull of Saturn varies. So it's actually stronger at periapsis than at apoapsis, and Titan gets stretched into a little bit more of a prolate ellipsoid, a kind of lemon shape. And Cassini's gravity measurements have been made, out here and near periapsis, and they're sensitive enough to actually register that change. I mean, it's only of the order of 10 meters of surface height difference, but it's what you would expect if the crust was isolated from the inside. So there is, we're all but certain, a water, probably with ammonia antifreeze in it, a water ocean in the interior of Titan, just like there are on most large icy satellites. Now, does that stuff ever get to the surface? Well, that's an interesting question. The ice crust on Titan is thicker than that on Europa. It's probably between 50 and 100 kilometers thick instead of the 15 on Europa. Can that material reach the surface? Well, it would have been much easier to reach the surface in Titan's early history. This crust would have been thinner in the past, for sure. We do see some interesting features on Titan's surface. These sort of blisters might indicate something having welled up from the inside. Geologists will debate that. The most persuasive is this feature called Doom Mons. There's something like a flow coming out of it. What's particularly persuasive is that there's a steep and deep pit right next to a mountain, which is something you see in volcanic areas like the Galapagos, for example. The pit is too steep to be an impact crater. So having a pit and a mountain doesn't guarantee it's a volcano. Having a flow come out of it doesn't guarantee it's a volcano, but it might be. Whether it's cryovolcanism or not, as I say, you can still get impact melt that will form liquid water on Titan's surface. There are actually relatively few craters on Titan because the surface is being rejuvenated by erosion. The same processes that make the sand dunes, the rivers, and so on are refreshing the surface in some respect. But there are a number of impact craters, and some of which are quite fresh. And these will have caused local melting of the ice crust and thereby the introduction of water, which would have persisted for tens of thousands of years before it froze solid. And that's a much longer timescale that we can do laboratory experiment. So something interesting may be in there. Just as an example, and to show that I spend far too much time on planes, I've actually seen 4 different impact craters from airplane windows on Earth. This is Manicouagan on the eastern side of Canada. It's about 100 kilometers across. There's actually a reservoir that defines it quite nicely. And there's actually quite extensive melt deposits on this crater that form actually columnar jointing. It's really quite a spectacular feature. Okay, let's talk about the other kind of liquid on Titan. We know that on Earth you can execute these life functions in liquid water, in a polar solvent. We do not know what all the possibilities are in a non-polar solvent, in liquid methane, liquid ethane. It's speculative, but we don't know it's impossible. That said, the hydrological cycle on Titan is interesting to study in its own right. I don't think I need to tell people in Houston that torrential rainfall and flooding can be a concern. And the fundamental physics is the same on Titan as on the Earth. The Titan being a body with a different temperature, different vapor pressure of the liquid, is an instructive laboratory. We have theories that explain how cloud convection works, for example, and they work for Earth today and Titan today, then we can be a lot more secure in how those theories are fundamentally correct and can replicate conditions that are different from today's, as, for example, our own atmosphere evolved. Titan is actually a kind of extreme example. I like to say Titan is to the hydrological cycle what Venus is to the greenhouse effect. It's sort of a terrestrial situation taken to an extreme. We believe on Titan the rain is actually quite rare, but when it does happen, it's torrential. Basically, the atmosphere can hold lots and lots of moisture, and so even though the sunlight is not very strong, the rate at which you evaporate material from the surface is slow. That means it just takes a very long time for the atmosphere to recharge with moisture. But when it does, it dumps out a fraction of what it can hold, and because it can hold so much, you may get tens of centimeters, even meters of rainfall falling in a single storm. It might be centuries before the next storm, but it can be really quite an important agent of surface modification. And we see river channels on Titan. We've seen clouds come and go. We've seen areas on Titan's surface get dark after there have been clouds there, suggesting that the ground has become wet, damp with methane, and then it's subsequently dried out. So the hydrological cycle is active today, and we can observe it in action. Now, we expected perhaps to find liquid on Titan. The methane in Titan's atmosphere should be destroyed in quite a short time scale, 10 million years, and yet it's still there. So is it being buffered somehow, or are we just looking at an unusual moment in Titan's history? And it was actually 2 years into the Cassini mission before we found surface liquids standing. We saw these river channels. It had rained sometime in the past. We knew that the ground at the Huygens landing site was actually damp, but we didn't see standing bodies of liquid until we looked at the North Pole. This was still in winter darkness at the time, 2006, but we saw these lake-shaped pits with radar dark material consistent with the liquid hydrocarbons in the base. There are actually a number of pits without liquid in them, so maybe there's been filling and emptying. You can, as the sun rose, as we moved through Titan seasons through the Cassini mission, past spring equinox in 2009 and into northern summer, we can start seeing the lakes with the Cassini's camera. This is actually an image in the near infrared. 940 nanometers is basically the same wavelength that your TV remote control has. It's kind of like light. The human eye just doesn't quite get there. And the seas are dark, and they're extensive. These are cloud bands, by the way. And when we map out the seas, and this is now a radar image again, we find that the largest of them is about 1,000 kilometers across. This one, Ligeia, is about 400 kilometers, and I'll come back to the depth, but basically this stuff adds up to between 100 and 1,000 times of the proven fossil fuel reserves on Earth. And the stuff that's in here is the same stuff that's schlepped around in these LNG tankers. There's about 300 of these tankers worldwide, and each cost about the same amount as a space mission, just FYI. But they're basically full of liquid methane at about 100 Kelvin, so more or less the same conditions as Titan's surface. This is actually a somewhat familiar material in engineering terms. One of the big surprises was that there's these extensive seas around the North Pole and hardly anything around the south. There's just one sad little lake. Well, it's not little, it's 200 kilometers long, called Ontario Lacus. There's a whole story about how features are named on planets. Lakes on Titan are named after lakes on the Earth, which one day will get confusing, I think. The seas are named after mythical sea monsters. There's 3 of them, Kraken, Ligeia, and Pungamare. But there's no obvious reason in the terrain that says all the liquid should be in the north. But we think it's meteorological. Remember I said that the orbit of Saturn around the sun is eccentric. That means that when you look at how much sunlight falls as a function of latitude and season, southern summer is shorter but much more intense than the north, and that at the present day, and that has the effect probably of distilling over any volatile material, basically drying out the south, and the liquids accumulate at the north. Now, 30,000 years ago, the opposite would have been true. There are Kroll-Milankovitch cycles like those that drive our ice ages or make the layered terrain around the polar caps of Mars. So there's some very interesting, comparative climatology you can do, looking at Titan, comparing with Venus, with Mars and the Earth. But there's probably a complicated history of where the liquids have been on Titan. And we see evidence of that in the geology. This is a close-up of Ligeia. It's again about 400 kilometers across. This is a radar mosaic. And you can see this sort of very, very crenulated coastline, right? And you see exactly the same thing in areas of the Earth where the land is sinking or the sea has been rising. This is the Mosaic Peninsula off the north coast of Oman. And you can see, basically there's these sort of skeletal mountain ranges with valleys between them that have been flooded by the sea. Here the Arabian plate is diving under the Eurasian plate at about 1 centimeter a year, and so the land is sinking relative to the sea. Now on Titan we don't know which of those possibilities is the case. You see a lot of that kind of terrain on the southern margins, but not so much on the north. So, is the land tilting? Is it a tectonic thing, or is it just that the sea has been filling up? We don't know, but the filling up would be consistent with this climate cycle idea. You can see the same sort of thing actually at near Las Vegas, Lake Mead. And this was a TV shoot I did with the BBC a few years ago. So I'm gesticulating out of the open door of the helicopter at the flooded valleys here that have the same sort of morphology. In this case, of course, it's because we built the Hoover Dam and the Lake Mead filled up. But what you can also see is this thing, this bright line here, which we sort of call a bathtub ring. And that's evidence that the recent lake level has dropped, in part because of water use and climate change. And basically the salts, the minerals that are dissolved in the water, have been plated out as the water has dried up and left this mineral deposit and evaporate. I think this black line actually is some weird interaction of how the rotor blades of the helicopter were chopping the light from the sun and how that interacted with the readout of the TV camera. The sound guy on this shoot, we're all crammed in the helicopter, asked the pilot if he could slow the rotor blades down because the sound. I couldn't tell if he was being serious or not. But we'll come back to rotor blades in due course. The seas have actually been strikingly smooth. We've got measurements. There's sort of clever signal processing voodoo you can do with radar to show that the sea level is very flat. Sea surface is very flat. In fact, to within a couple of millimeters. There are a few occasions when Cassini has flown by Titan that its infrared instrument, which is able to see through the hazy atmosphere even better than that 940 nanometer camera picture could, and has seen the reflection of the sun on the lake surfaces. And you can only get such a strong reflection if the sea surface is mirror smooth. So, this is sort of an interesting question. How do you generate waves in liquid hydrocarbons, which have a different viscosity, different density, the gravity is different, the atmosphere is thicker? You can start, nobody's really thought of that before, right? Because on Earth, all you have to worry about is air and water. I did do an experiment back in 2004 in a wind tunnel at NASA's Ames Research Center. It's actually a Mars wind tunnel. They can pump the air pressure down to Mars pressures, and we explored the variation of wave generation with pressure, and you can sort of try to extrapolate that up to the Titan's pressure, which is 1.5 times Earth. When nobody was looking, I substituted this tray of water with one of kerosene, and you find that the lower density and viscosity of a hydrocarbon liquid lets waves grow, as you'd expect, easier under these conditions than is the case for water. So it should be easy to make waves on Titan. And we haven't seen them. So what's going on? Well, could it be that the liquid is kind of tarry? It's not very clean methane, but it's full of propane and butane and hydrogen cyanide and acetonitrile and everything else that makes it kind of goopy. Or maybe the wind just isn't strong enough. We know the wind is strong enough to make sand dunes on Titan, and it turns out if you figure the math out, maybe 1/2 to 3/4 of a meter per second is enough to make waves on Titan. And looking in the northern hemisphere, we have wind models that predict how strong the winds should be as a function of season and latitude. And at least in the early part of the Cassini mission in the north, the winds were simply too weak. Now, the models say that around about 2014, 2015, the winds should have gotten strong enough to start causing waves. And we haven't really seen that. So, is the wind, the threshold wind to generate waves actually much higher? I don't know. Are the models wrong? Probably, they're just models. But that's the great thing about scientific progress. That's how you know that there's something missing, is when the model doesn't predict reality. So, whether it's something to do with Titan's terrain, or perhaps the soil moisture is affecting the temperature rise in response to the changing seasons. These things have to be fiddled in the models. We have to get the models right. We don't have a lot of data to constrain them. You can also just have calm days in the windy season. We need to look at the statistical significance of how often we've looked and how much wave or non-wave activity we've seen. But it's an interesting problem. Okay, We have actually seen with the radar a couple of patches on the surface of Ligeia where brightness has come and gone. And the most likely explanation is sea surface roughness. Now, you can get little patches of roughness just if the wind is just at the wave generation threshold, call it cat's paw. You just see these little patches of roughening. There may be something else going on. It could be this area is shallow and gets rough when there's a strong current. You get wind-generated currents as well as tidal currents on Titan. The occurrences of these are not synchronized to the tides, as far as we can tell. So probably it's wind. We don't know, but it's an interesting mystery. As I mentioned, the lakes are named after lakes on Earth. Seas are named after sea monsters. I did a submarine study that we'll come back to later that kind of postulated a voyage around the seas. And when we start plotting that sort of thing out, you have to start naming things. And they decided to name inlets on Titan after inlets and bays on the Earth. And turns out one of the most interesting ones is one from where I'm from, Scotland. This is called Moray Sinus, after the Moray Firth. And we've seen it change brightness, radar brightness too, again, perhaps indicating some sort of currents, flows in and out. So the seas aren't stagnant. We wouldn't expect them to be. But extraterrestrial oceanography is still a science in its infancy. We actually have the remarkable benefit of knowing how deep the seas are. It turns out that liquid methane is very radio transparent. Cassini's radar can make pictures like this in its imaging mode, but it can also look straight down and measure surface heights. It's actually a very sensitive way of measuring roughness and waves. But when we had the radar in this mode going across Ligeia back in 2011, we got a very strong echo from the sea surface because it was so flat. It's like a mirror. But we got a second echo, about 1,000 times weaker, 2 microseconds later. And if you figure out the propagation speed of electromagnetic radiation in liquid methane, that corresponds to about 160 meters down, which is remarkable. There's a very narrow range of transparency and depth space where we could actually pull out this echo. If it's too shallow, the bottom echo merges with the surface one. And if the sea is too deep, the echo gets too faint because it gets absorbed by the liquid. We haven't seen an echo from the big sea, Kraken Mare, but we did get this very nice measurement of the depth. And that's why we can say there's 200 times the fossil fuel reserves on Titan. So now that we have a depth measurement and we can kind of scale the unknown depths of Kraken to what we see at Ligeia, we can plug the Titan tidal cycle, the gravitational accelerations due to Saturn, into a model and see what happens. And we should get tides of a few tens of centimeters on Titan, and that corresponds in the open ocean to probably flow velocities of 1 centimeter per second or so, not very much. But there are a few places, some constrictions, where the tidal currents may get accelerated. And the most prominent of these is in the southern part of Kraken Mare. I nicknamed this the throat of Kraken, but it's now been given an official name. So the straits or narrows on Titan are named after characters in the Isaac Asimov Foundation novels. This is actually Selden Fratum. And the currents in here could be 0.5 meter per second, because there's about 20 cubic kilometers of liquid has to go through this labyrinth of channels. This is actually about the same size as the Straits of Gibraltar, if that means anything to you. And 0.5 meter per second is actually enough to generate roughness. And there's been some evidence of that in Cassini data. And another field photo. This is actually my wife and I went on holiday here. This is a tidal channel between the Isle of Jura and the coast of Scotland called the Corryvreckan. So this is a perfectly calm day. There aren't waves here. This is rough water caused by the tidal currents, interacting with the seabed topography, and there's whirlpools and stuff. Actually, George Orwell wrote 1984 in a cottage about 12 miles away, and you could hear the tidal currents in this stuff. So Titan might have some of that going on. The tidal mixing in these straits may control how much exchange of liquid there is between the tidal basins. When we look at the output of the global circulation models, they tell us there should be more rainfall at the highest latitudes. So, Ligeia Mare and Punga Mare are up near the North Pole. They should get rain, which is basically pure methane. Now, there can be, ethane and propane and butane and all the other stuff dissolved in Titan seas, so basically have the same function as salt, and they actually may plate out to form evaporite deposits, when we've seen some evidence of those. So it may be that the extra rain you have at the highest latitudes introduces fresh water, pure methane, into Punga and Ligeia, and they get basically flush the salts, the ethane and everything else, into Kraken Mare. And so Kraken may be quote-unquote saltier, more ethane-rich than Ligeia and Punga. And that may be why we don't see a bottom echo, because these other compounds are more radar absorbing. So this is actually the same sort of arrangement as you have with the Aral Sea, sorry, not the Aral Sea, the Sea of Azov and the Black Sea, which are brackish and relatively fresh, flushing their salts into the Mediterranean. You get more evaporation at the lowest latitudes, and so this is again evidence of the ongoing hydrological cycle. But it's this recurring theme with Titan. You've got a terrestrial process working with different materials under different conditions, and it's really fun to just sort of transport your mind and figure out how this all works. As I mentioned, we don't know what kind of chemistry could go on in these kind of solvents. We don't know whether there's anything that can perform the metabolism and the information storage and replication that DNA does in water. We do know at least that the function of isolation, of forming a membrane or a liposome, can be done in liquid methane with a compound called acrylonitrile. And we know that compound exists on Titan. It's been detected by actually radio telescopes, the ALMA array. The other stuff, we don't know. It'd be interesting to go there and find out. So Cassini came to an end, as you heard, after 126 flybys of Titan, and again, you can read all about it. The scorecard had many Enceladus flybys, as you may have heard a few weeks ago. We've learned an awful lot from all this, but it's definitely time to think about the next steps. Cassini is gone, but people were thinking about the next steps already 20 years ago. One of the obvious things you can do on a world with a thick atmosphere is float. And some of the work in the late 90s was focused on airships. I actually had the chance to fly in one in 92, a little pedal-powered thing. It was just magical. You just kind of winch your weight back and forth to tip the envelope up or down, and then pedal, and it drives this propeller, and it's just perfect three-dimensional freedom. Airships went out of fashion for Titan. Montgolfier's hot air balloons got a careful look about a decade ago. One of the fun things you can do is use the waste heat from a radioisotope power supply. Because there's so little sunlight, you need a radioisotope power supply for electrical power for any kind of long duration mission. And these sources provide a lot of waste heat as well as the electricity. And that waste heat could keep the gas warm and give you buoyancy. And you could change the buoyancy and go up and down, and you exploit the winds. You could circumnavigate Titan a couple of times in a year. But it's always hard to be totally sure that a balloon will do what you want it to do. Balloons are great for anniversaries and sightseeing, but if you really need to go somewhere and have the thing work, maybe heavier than air flight is the way to go. But it was certainly fun to actually take a fresh look at ballooning because it's been around for a couple of centuries almost. It's all very empirical. You ask a balloonist, how much power do you need to fly 100 kilograms of scientific payload? They don't know. They know if you have 3 people in the balloon, you need one of these propane things for about an hour of flying. It's just kind of ad hoc. So it's fun to actually calculate what the power metrics are for a system like this. You can imagine landing on the surface of Titan, as Huygens did. It wasn't actually guaranteed to survive landing. It was just good luck that it landed somewhere nice and soft. Much of Titan actually may be nice and soft. We imagined a sort of Mars Pathfinder kind of lander to land on the dunes. If you landed on a dune, you just roll down to the bottom and then unfurl the petals. That would be easy to do. You can imagine going into orbit around Saturn. Cassini's observations of Titan were not limited by the capability of its instruments, but by the fact it was in orbit around Saturn and it just whipped by Titan once in a while. If you had a Titan orbiter, in the first 2 weeks, you'd have had more observing opportunity than Cassini has of Titan in the 13 years it was there. But the really exciting stuff is in situ. Titan is an environment you can imagine exploring with a vehicle in that environment. And there was a proposal that went a fair way towards implementation about 5 years ago. I was involved in basically a kind of like a big version of the Huygens probe, but with a radioisotope power source. And Huygens was actually designed to float, but we didn't know where the seas were. It landed in the equatorial deserts near the dunes. But now that we know where the seas are, we could target this to Ligeia Mare. And it wasn't just a paper study. We did splashdown tests, which were really kind of interesting. Probably the biggest series of splashdown tests, albeit with a scale model, since Apollo. It was actually really kind of interesting. We tested sonars in liquid nitrogen. Sonar is not a typical spacecraft kind of instrument. Obviously, in space, no one can hear you ping. But it turns out, actually, using the same piezoelectric from the Huygens penetrometer, the sonar transducers work great under these conditions. And where I work, APL actually does a lot of work for the US Navy, and so we have sonar experts, which was handy. We simulated how the vehicle would respond to the waves. We had to predict the waves. That was an interesting exercise. Unfortunately, NASA elected not to pursue this idea, and instead is flying the InSight mission to Mars. There's been some blue sky thinking. How would you explore the seas? Could you have a submersible? That's probably a little beyond what we're able to tackle securely right now. But just over a month ago, NASA selected a proposal from APL, one I played a big role in formulating. My wife is actually the principal investigator, called Dragonfly. It's a relocatable lander, right? It's a lot like the Mars rover Curiosity in size, or the Phoenix lander. We have a couple of drills to acquire a surface sample. We'll suck the material up with a pneumatic transfer system, because we can use the Titan atmosphere to convey material, basically like a Dyson vacuum cleaner. We have a little cyclone separator to pull the bits out. We'd land using rotors to provide thrust, pull up this high gain antenna and send the data back to Earth. And then after we've explored one landing site to our satisfaction, we can just fold the antenna down, spin up the rotors, take off and fly again. We have to fly with a big battery, right? It takes us all of a Titan night to recharge it. But that's what the Titan night is for. We can't communicate to the lander while it's on the other side of Titan. So it might as well charge up the battery. So we are in the next 11 months or so to flesh out this concept with the hope of launching in 2025 and landing in 2034, and then again and again and again. It's really quite transformative capability, and will let us seek out those places where we think Titan's organics have interacted with liquid water. So there's a tremendous capability. And this thing in one flight of 1 or 2 hours duration, will fly farther than any of the Mars rovers have ever driven. And we can fly, once a Titan day. So I think I'm way out of time. Titan has an internal water ocean, we believe, but it has rich organics on its surface as well. And those things have probably interacted in interesting ways. Separately, there are hydrocarbon seas that are analogous to our own surface seas of water, and they do things like have waves and tides and all that. Titan is a wonderful place to explore because of its low gravity and thick atmosphere. You can imagine pretty much any kind of vehicle exploring Titan. So there's a lot of possibilities, and we're exploring one of those in some detail now. Thank you.
Okay, well, time for Q&A. So raise your hand and we'll hand you a mic, and please use the mic so everybody can hear, because we're also recording. Who wants to go first?
Stunned silence.
Wow, you did so well.
With the prospect of floating around in such cold liquids, generally the thermal transfer is always a hard problem, even in a vacuum where you're just radiating. But if you had the conduction into the liquid, would that present special engineering problems?
Yes and no. So in fact, it's the same problem Huygens confronted. At these low temperatures, radiation basically doesn't transfer any heat at all. And the atmosphere is sufficiently thick and cold that all of the outer surfaces of Huygens were quenched to about 94 Kelvin, maybe 96, relatively quickly. And so Huygens had a 5 centimeter thick layer of foam insulation that basically limits the heat transfer. I mean, it was, the interior was benign, room temperature, freezing point, something like that, and outside is 94 Kelvin. So it was losing about 350 watts of heat to maintain that differential. So any long-term system at Titan has to buffer that loss. And that's why the radioisotope systems are so important, because they have that waste heat available. But you basically, the engineering solution is that you insulate.
NASA is testing Krusty, kilopower reactor using Stirling technology. That's a real reactor, fission reactor that can supply kilowatts of electric power. How big a dragonfly could use that? And how big a rocket would it take to move that to Titan?
That's a great question. And I was actually involved in a study last summer looking at a Titan lander using the Pathfinder-like one I mentioned as a starting point, but substituting a kilopower fission power source. It turns out it's actually a rather bad fit. Landers, basically the starting point is that energy need more or less maps to data, right? Every bit of data you send back to Earth costs about 10 millijoules per astronomical unit. And a lander, because it's sitting in one place, it can only see so many pixels of landscape, and it can only drill, the ground a small number of times and analyze the stuff before you've basically done everything you're going to do there. So the total number of bits you can acquire is limited. As to set the context, the Viking landers worked with radioisotope power systems on 70 watts. It turns out landers actually need a lot less power than orbiters, because orbiters have to keep the fuel tanks warm, they have to run the valves, the attitude control, GNC all has to be running, whereas a lander can just sit there and turn everything off. And actually on Dragonfly, that's what we do during the night, because we want the energy to recharge the battery. So if we had, let's say, a 200 watt power supply, well, that would be great. We could charge up the battery faster. We could fly, 2 hours, 3 hours in a Titan day instead of just one. But it doesn't qualitatively change the picture. Now, an orbiter, because it's flying over new terrain, every second, you can have a more powerful camera or a more powerful radar or spectrometer. You can generate kilobits a second, megabits a second, and it takes kilowatts to send all that data back. So a reactor would actually be a good fit for an orbiter, but a less good fit for a Titan surface system, unless you're trying to fly continuously. And there was actually an idea in 1992 by Bob Zubrin to do exactly that. May not be completely realistic. But excellent question. But in fact, for a landed system, a radioisotope power source is actually a better fit.
Are there any questions in the overflow room?
None, thank you.
About how much of Titan's surface is liquid compared to the solid?
Oh, yeah. It's not a lot. I think 2% is exposed liquid. I can't remember if I had that on the slide or not.
And what's the difference in the composition between the liquid versus solid surface?
So I never actually said what the solid surface is. There we go. C's cover only about 1%. So we don't actually know what the solid surface is. The expectation before Cassini arrived was that the crust would be dominated by water ice. That's probably still correct, just from cosmic abundance. We know the density of Titan as a whole, 1.88 grams per cubic centimeter, so it's probably half rock, half ice. All the rock probably sank towards the middle, and we've got the ice on top. But when we look with remote sensing instruments, most of the surface we see does not show the signature of ice, either in the microwave or in the few near-infrared windows we can see through the surface. Water ice does appear to be exposed in the ejector blankets around a couple of impact craters, and in some areas where fluvial erosion, the cobbles carved out by of streams, have exposed some material. So there's, for most of Titan's surface, there's a veneer of organic stuff. Now, as I say, the dunes seem to be a particularly pure example of that, but there seems to be organics more or less everywhere, except in a few exposures. Now, when we get closer to Titan and explore at a finer resolution than Cassini does, then I expect we would see a lot more heterogeneity. And that's where the mobility of something like Dragonfly could be really powerful, is that we can find the interesting rock.
Any more? All right, let's thank our speaker one more time.
Thank you.
And don't forget to join us out in the lobby for a reception. And continue to watch the website, our webpage. As soon as we have a date for our last talk, we'll post it there, and we'll also send out an email. So put your email down if you haven't done that yet. Thanks for coming.